Hi everybody and welcome to the CERIAS Security Seminar here at Purdue University. Today is my great pleasure to introduce Rahul Potharaju. Many of you probably have seen Rahul towards the beginning of the semester when he gave a presentation related to some of his work in finding plagiarism in mobile applications. And he really wanted me to insist that today he's going to present something else. Actually, he's here to tell you about some very recent work that he just presented last week at NSDI. And the title of his talk is Towards Automated Problem Inference from Network Trouble Tickets. You probably know Rahul is a student here. So if you have more questions, you can actually grab him after the talk. Rahul?
Thank you. Mic's on? Is mic on?
Oh, yes. How about now?
Perfect.
Okay, thanks. Good evening, everyone. As Christina mentioned, my name is Rahul, and I'm from the Computer Science Department here. In case you're wondering, again, as she mentioned, I'm not here to present any other follow-up work on the smartphone security work that I presented towards the beginning of the semester, but I'm rather here to talk about my second area of research, which entails natural language processing, ontology modeling, and data mining. So specifically, I will show you today how we have used some of the cross-domain techniques in improving network management. First, I will begin to motivate what is the background knowledge required to understand my talk, and then hopefully I will convince you that some of these techniques are indeed useful in other domains. I'll start off with everything, like a particular sentence that pretty much everyone says, that we are living in a cloud era, in fact. So Google calls them App Engine, whatever services they actually render. Microsoft calls it Azure, or Amazon calls it EC2. No matter what they call it, it is very clear that these services have brought about a technical shift in computing, especially in the paradigms that they introduced. Nowadays, we are looking at designing massively scalable data centers that can host hundreds of thousands of devices efficiently and robustly. And software as a service is becoming popular by the day. Most of the people are offloading their software to the cloud so that someone else can take care of their problems. And finally, big data analytics is now a reality to the common user. You can offload computation to thousands and thousands of machines, and you can expect it to finish in under a minute or under an hour. However, like one recent trend that has been very popular is the commercialization of these services, in fact. So if a corporate environment should sustain with all these paradigms, or if they should be successful, then there are certain critical aspects that they need to take care of, especially dependability. How reliable or available can their cloud services be? Can they offer clients a sentence such as, our entire service will be down only for 1 hour in a given year? Can they say such statements? And the second one is security. Can they protect users from other users who are also using the same cloud services? And finally, privacy. Now, what happens in such massively complex systems is that problems are inevitable. Problems keep rising up. So the next natural question that arises is, how are these problems fixed? Usually what happens is the cloud provider makes an agreement with a third-party service provider. So he provides a list of service requirements, which the third-party service provider reciprocates using the service delivery, in fact. Now, how does this agreement look like? The third-party provider could, I apologize for the small font size, but the third-party provider would provide certain guarantees on the turnaround time, for instance. What that means is what is the time that it takes for this provider to detect that a problem even exists? And the other metrics could be mean time to repair. How long will the provider take to repair any given problem on an average? So usually this is about 15 minutes or 5 minutes, in fact, and the motivation for that will be clear shortly. So this entire agreement which goes on between these two people is collectively termed as a service level agreement. Now, The next question perhaps is, how are these service level agreements met? There is a troubleshooting team. So I was mentioning this third-party service providers. These people actually offload this responsibility to a troubleshooting team that sits on top of your cloud. So they keep monitoring your cloud, and they keep monitoring different data sources that are monitoring your cloud service, in fact. For instance, workflow reports or syslogs. So if you're familiar with networking, you may have heard that syslogs will keep track of whatever is going on in the network that you are actually maintaining, and traffic logs and network alerts. What really happens is, when an alert is generated from any of these systems, the troubleshooting team logs a ticket to one of the trouble ticketing system. Especially think of this trouble ticketing system and something in some sense that you know. How many of you have called up a call center, like a customer care? Whenever they start trying to solve your problem, what you cannot observe is that they will start opening a trouble ticket in which they will record each and every step that they have taken with you to solve the problem. So having said that, they log this ticket into a trouble ticketing system, and then if they are unable to solve the problem, but they know what the problem is, they will do what is called as an escalation. They escalate this problem to another team called the network escalations, which is a set of highly specialized operators who are very much trained in solving these problems. And even these escalation operators will continue to log more information to the trouble ticketing system. And finally, if the troubleshooting team doesn't even know what the problem is, it goes to a different team called the network incident analyst team. These people are specialists in diagnostics. They do debugging, and they try to figure out what the problem is, and then they escalate the problem to the network escalations team, who will then resolve the problem, in fact. So as you can see, there is a multi-tier hierarchy that is going on, in fact. The reason being that they want to minimize the system downtime. Now you might ask me, why bother about system downtime? Why is it so important? The answer lies in some of the recent studies that were conducted, where Information Week found out that IT downtime costs about $26 billion per year. And there are other studies that show that for every minute of downtime in your cloud, back in 2004, this cost was about $700 per minute. Now that cost in 2011 has increased to $5,600. Now imagine we are living in 2013. I'm expecting this to be much, much higher than before. So given all these problems, like you can now start seeing that a minute of downtime will cost heavily on the side of the cloud provider. So they have every incentive in actually minimizing this downtime. Now, how do they minimize this downtime? There are various techniques in place. One is improve system architecture. So whenever I'm building an architecture, I will always use extremely reliable components to build the architecture itself, so that the mean time to failure is very high, and therefore I can expect a robust architecture. The other approach is to introduce redundancy. Whenever you're deploying a router, instead of deploying one router, I would deploy 2 or more routers, so that even if one fails, the other will catch up to complete the responsibility. And finally, the third one is, I can go ahead and improve incident response and management. That is, when a problem occurs, how do you quickly go identify what the problem is, and how do you quickly resolve it? In fact, that is what is entailed in the third one. So today I'm going to focus on the third part. How do you minimize downtime by learning from mistakes, in fact, whatever you have done in the past. Towards this end, I will be presenting one of our recent works, as Christina mentioned, on specifically network trouble tickets. So the trouble tickets, as I mentioned earlier, are of different varieties. You can have trouble tickets inside call centers, you can have it inside some other systems. This is specifically on data center networks, essentially. What are the problems that these people observe? So there were 2 motivations behind this effort. First, when a problem occurs, the focus within the current data center environments is to quickly fix the problem and move on to the next one without understanding the big problem trends. Therefore, we want to analyze these network trouble tickets to understand and uncover these big problem trends, in fact. Second, we want to be able to learn from our mistakes and apply the lessons that we learn towards improving network management. This is a joint work with Navendu from Microsoft Research and my advisor Christina from Purdue. Let me start off by showing you how network troubleshooting is done today. Sure, I have given you a big picture overview, but now I'll dig into the details and tell you how this happens in reality. Our focus is specifically on data center environments, as I mentioned, which consist of thousands and thousands of routers and switches. Let's do this by induction. In such an environment, let's consider two devices that are connected by a link. When this link goes down, it generates an alert that is logged in a network monitoring system. This, in turn, triggers an alarm to an operator console. This operator console has, as I was mentioning, operators kind of monitoring for emergency events and all. So these operators maintain network trouble tickets to keep track of all the debugging steps that they have been doing so far to fix the problem. So think of these network trouble tickets really as diaries written by these network operators during troubleshooting. Our goal is to analyze these diaries to extract key information and learn from those mistakes, if we have done any, to improve network management. To achieve this, we want to extract three key features from a given ticket: problems, activities, and actions. What do these mean? First, what problems were observed? Like I was mentioning, everything is inside the tickets. So the first important thing I want to look at is what are the problems observed. For instance, did the operator notice that the device got stuck in a reboot loops where it is continuously rebooting? Or did he experience that the device itself failed? The second one is, what activities were performed as part of debugging? Did the operator check for any configuration changes? Or did he verify the existence of valid routes in the routing table as part of fixing the problem? And third, what was the resolution applied? What was done to fix the problem? For instance, did they replace the network card, or did they just end up replacing the entire device? Therefore, given a ticket, we want to extract problems, activities, and actions. The idea is that having these as building blocks, we want to answer higher order questions. Our first question concerns redundancy, which is a common technique used to mask failures. Why does it fail? Was it due to misconfigurations, or was it humans making errors? Our second question is, what are the components that fail frequently within routers and switches? Is it network cards like I was mentioning, or is it memory, or is it software, which is the main culprit? And finally, are new devices more reliable? On one hand, essentially, these newer generation devices offer you higher capacity along with a variety of new features. But does that mean that they also offer higher reliability? That is the question we want to investigate. In the later part of my talk, I will show you how our system is able to answer these questions. But before that, let me show you what information a ticket contains in the first place to make this possible. And I'd like to mention, so if any of you have any questions, I'd like to keep this talk interactive, so please interrupt me at any point to ask any questions. So trouble tickets comprise two parts. First, structured fields, and second, free-form text. Look at this example. The top part of the slide is showing you structured fields, like ticket title, problem type, problem subtype, and so on and so forth. These structured fields are either automatically populated by a system that has rules defined inside it, or the operator will start populating them whenever he observes a problem. The other part is free-form text, which contains a variety of elements, such as email exchanges between operators, IM conversations, device debug logs, and so on and so forth. Our goal is to utilize this information to extract three key features, like I was mentioning: problems, activities, and actions from a given ticket. Now, what makes this problem fundamentally hard are two key challenges. First, structured fields are often coarse-grained or inaccurate and incomplete. In a large measurement study that we conducted, we observed this to be the case in 69% to 75% of the tickets, which means that these structured fields cannot be used for any kind of inference. The other part is free-form text. Like I mentioned, it contains a variety of elements, email exchanges, IM conversations and all, written in natural language, and as you might expect, numerous typos, ambiguities, grammatical errors, and they contain domain-specific words, which may not even exist in the dictionary. So if you don't know what words you're looking at, how will you understand them? That's the fundamental question. Overall, structured fields cannot be used for inference due to their high inaccuracy, and if we use them, we risk making the wrong decisions. Therefore, our focus is on analyzing this free-form text to extract problems, activities, and actions. To achieve this goal, we make 3 key contributions. First, we performed a large-scale study on over 10,000 tickets to analyze the challenges in mining these tickets. Our main results are that structured fields are highly inaccurate and are not suitable for inference. And the structure of free-form text makes it challenging to analyze them. To address these challenges, we built a system NetSieve that takes a semantic-based approach towards problem inference. In particular, NetSieve extracts 3 key features from a given ticket, like I was mentioning. First, what problems were observed? For instance, did the operator observe a firewall failure or a firmware error inside the given ticket? Second, what steps were taken during debugging the problem? Did they basically check if the configuration file was changed recently? Or did they verify the existence of valid routes? And third, what were the actions taken to resolve the problem? Did they replace a network card or did they just replace the entire device? We evaluated NetSieve on a large ticket dataset and our results are reasonable, in fact. Till now, I have presented the context of this problem. Hopefully, I convinced you that trouble tickets contain some useful information that is worth exploring, in fact. And I've also presented our specific problem of analyzing network trouble tickets. Now, I will show you the challenges in effectively using strawman approaches to solve the same problem. Next, I will show you our system NetSieve that takes a semantic-based approach to solve this problem. Finally, I'll present our evaluation results and conclude. Before I present our results, remember that our key goal is to extract problems, activities, and actions. So it is worthwhile exploring existing approaches. Will they solve the problem? Note that some of these approaches have been used in the past with some success. The first approach is looking at the different structure of the trouble tickets. For instance, as I was mentioning, they have IM conversations, emails, device debug logs, and so on and so forth. So the first strawman is to use conventional natural language processing techniques out of the box and then try to see what can be done. But the fundamental problem there is these techniques are designed to work well only on well-written articles such as news articles, for instance. The second approach is to select a set of keywords and then do some inference. But it ignores contextual semantics. What do I mean by this? Consider the sentence in red. If you select cable as the keyword, you will miss the fact that it is a negation. The sentence specifically says don't replace the cable, but if you do a keyword-based selection, you will miss this out. Consider the sentence in blue. If you select maintenance, it is not really clear if the ticket is in fact due to maintenance or not, because the operator is specifically mentioning we are currently checking for maintenance, but it's not clear if it is indeed due to maintenance. The third approach is to cluster these tickets based on a set of keywords. So we give up on problem inference from a single ticket and we try to look at problem trends, in fact. However, note that this takes significant time and effort because you're not looking at 10 or 20 tickets. You're looking at tens of thousands of tickets. So you'll have to go through each and every ticket to find out what these list of important phrases are. And even if you successfully build this list, it risks becoming outdated, in fact, because the network keeps evolving, new types of devices get introduced, so you always risk having an outdated list. Now, I will show you how our system addresses these challenges, in fact. So the goal of NetSieve is, given a ticket, it wants to extract problems, activities, and actions. The system itself operates in 2 phases. First, we want to build a knowledge base that contains a list of important phrases in the current domain along with their semantic. what do I mean by semantic will be clear shortly. In the operational phase, which is the second phase, I want to use this knowledge base as a means to infer problems, activities, and actions from a given ticket. Let me first show you a bird's eye view of the system first, before I dig into each step in detail. I was mentioning knowledge base. Think of a knowledge base really as a technical dictionary. So given a ticket, you would look up each word, each phrase inside the technical dictionary to make some sense out of it, to attach a semantic out of it. Think about how we started learning language. If we don't know some word in a given text, we would refer the dictionary and try to understand what that means. NetSieve takes a similar approach. So the idea is, once we build this knowledge base aka technical dictionary, we can use this to infer problems, activities, and actions from a given trouble ticket. This is achieved in 3 steps. First, we extract frequently occurring phrases in the given input. The intuition is to find text that operators frequently use to describe problems across a large number of tickets, such as the power supply unit is faulty, or maybe access router is inoperative. There are only a couple of limited ways in which one can describe these problems. Once we have this, in the second step, we want to discover which of these phrases are important in the current domain. By domain, what I mean is, for instance, intuitively the way to understand is, we're now looking at the networking domain. Therefore, power supply unit is a word that may be important in the current domain, but some phrase like is to inform you that there may not be important, because we are not looking at general grammar. Therefore, the role of the second phase is to narrow down the list of important phrases. In the third phase, we want to attach a semantic to each of these domain-specific phrases. NetSieve achieves this using ontology modeling, where it takes each and every domain-specific phrase and attaches a meaning to this phrase. So for instance, the power supply unit is tagged as an entity, and faulty, which is a state, is tagged as a state. Therefore, given these 2 words, you will now understand that there is an entity and there is a state associated with the entity. Similarly, you have access router, which is also again a physical device that is tagged as an entity, and inoperative, intuitively thinking it's a condition of the entity called access router, and so on and so forth. So to summarize, we first extract frequently occurring phrases, then find out which of these phrases is important in the current domain, and finally attach a meaning to each of these domain-specific phrases. Simple enough. Now let me dig into each step in detail to explain what we've done. Our first step is to find frequently occurring phrases. The intuition, as I mentioned, was to find text that operators frequently use to describe problems across a large number of tickets. This problem is equivalent to extracting all possible n-grams, where an n-gram is a contiguous sequence of n words. However, when we tried utilizing existing approaches for n-gram extraction from natural language processing, we found several challenges. First, they were computationally expensive. Second, these tools have numerous thresholds that are difficult to tune. And third, not all n-grams are useful, as some of them constitute noise. I'll show you what I mean in the next slide. Therefore, our key idea to solve this problem is to trade completeness for scalability. What do I mean by this? Specifically, given the input set of tickets, we apply a compression algorithm to extract a list of repeated phrases. The intuition is that compression algorithms are extremely good at detecting the redundancy inside the given input. And they do this by constructing an encoder, which is typically called a dictionary. Therefore, our goal is to apply a compression algorithm. In this case, we applied LZW to the input, obtained its encoder that contains all this list of repeated phrases, and then move on to the next stage. This list of repeated phrases does not contain the frequencies, in fact. Therefore, what we do is we apply a second step to compute this frequency using a routine string matching algorithm. Therefore, at the end of this stage, we have a list of repeated phrases along with their frequencies. These are some examples of repeated phrases that we find. We found like several types of these phrases. For instance, frequent message templates. Most often what happens is in time-critical environments, operators generally have templates that they usually have in a notepad file that they copy-paste for every single problem. So for instance, the first one, team, this is to inform you that there has been some kind of a network incident. So in problem inference, this may or may not be useful, but that is what the stage extracts, a list of repeated phrases. Some are logging messages of the type error 0, collision 0, which are from device debug logs. So this is what this stage extracts. In the second stage, we want to find out which of these phrases are important in the current domain. So recall that our current domain is again networking, in fact. However, how do you filter these meaningful phrases? Sure, I can give you a million phrases and ask you to pick the important phrases, but how do you do that? One obvious strawman is to leverage the help of a domain expert and ask him to label each and every phrase. But that is significantly time consuming, considering that I'm expecting millions and millions of phrases. Therefore, our idea here is to apply a set of linguistic filters first to pretty much filter down the list and then rank the remaining phrases using information theoretic measures. So by applying these filters, what really happens is, consider the example on the right. The first three phrases get marked as important, the rest as noise, because they are not technical words and they are not useful in inferring any kind of problems from the current domain. By using these filters, we were able to reduce noise by several orders of magnitude. We started off with roughly 19 million phrases. We ended up with about 5,600 important phrases, which we give to a domain expert for labeling. Now, of course, we face the philosophical question. How do you define meaning of a domain-specific phrase? For instance, consider the example on the right. Given a phrase such as "and replace line card," what does replace mean? And what does line card mean? And if I put these two words together as replace and line card, what is the relationship that I would like to establish between them? Netweave solves this problem by using ontology modeling. Similar to object-oriented programming, at least for those of us who don't come from natural language processing, the way to understand this is similar to object-oriented programming, where we define a set of classes. Netweave also defines a set of ontology classes, which can be used to tag each of these domain-specific phrases with one particular class label. The idea is that given such a set of rules or an ontology model to a domain expert, he will now be able to tag the given input with certain class labels. To give you an idea, let me choose three different classes from our ontology model: entity, action, and condition. Think of entities really as nouns in a sentence. Given a sentence, sure, you can find entities. These are objects that can be deployed or repaired. For instance, consider a core router or maybe a flash memory. These are physical objects that you can touch. Think of actions as verbs. For instance, they are behavior that can be caused upon an entity. For instance, if you take the words reboot and replace, I can always say that the core router was rebooted, where reboot is an action that happened on top of an entity called a core router. By the way, core router is just a fancy name for another kind of a router. And finally, think of conditions as adjectives. They describe the state of an entity. So I could say something like bit errors or a hung state. So if I want to say that the core router is in a hung state, it describes the condition of a particular entity. The idea is that given this model, the domain expert can now tag the input as replace can be tagged as an action, and line card can be tagged as an entity. Let me summarize. In the first step, we extracted frequently occurring phrases. Now in the second, we figured out which of these phrases are important in the current domain. And finally, in this step, we tagged each of these domain-specific phrases with a class label that we use to make some inference. Let me put all of this together. Sure.
So in the previous slide that you had, your action, you also classify negation?
Yes.
As so it's a phrase, so it's just not a word,
phrase,
right?
yes.
Okay.
We use simple negation detection, but of course, NetSieve also relies on some natural language processing, standard natural language processing techniques, so it is subject to some of their limitations too. So, now let me put all of this together. So far we've looked at what are the different steps in extracting something called as a knowledge base. Now what exactly does this knowledge base contain? First, it contains an ontology model, like I was mentioning. This ontology model is a taxonomy of ontology classes. What do I mean by that? I've shown you 3 such examples from my ontology model: entity, action, and conditions. But in the real model, entities can be subdivided into replaceable entities, such as physical devices, maybe like routers or switches, and virtual entities. For instance, software. Software is something that you cannot touch, but you can still replace software or upgrade it. And actions. Actions can be again divided into different types. Physical action is something like replace or reboot. You physically go to a location and then reboot it, right? And maintenance action is something like verification. Is the cable properly connected? Sure, even that is a physical action, but the domain expert in this particular domain decided to do this kind of a taxonomy division. Therefore, this brings up a very important point, that the ontology model is dependent on who is doing the ontology design. So if I do it, I will probably put up one ontology model. If you do it, you might come up with something different. Therefore, in order to do this, we took the help from multiple operators who kind of consistently agreed in the end that, okay, this is the best model that we can come up with. The second is ontology mappings. What does that mean? Each domain-specific phrase is now tagged with an ontology class label. Therefore, something like a load balancer, which is a device in data centers, is tagged as an entity. Inoperative, as I was mentioning, is a problem condition. There are different conditions. For instance, amber is just describing the state of a light. So that is not a problem condition, in fact. And failure is another problem condition, and so on and so forth. And finally, you have a list of synonyms. The problem with natural text is that you and I can use different set of words to represent the same phrase. For instance, power supply unit or power supply units or even PSUs all mention the same thing. So what we have is a database consisting of frequently used synonyms. Therefore, if someone is using fiber and fiber, like as in US English and UK English, we will convert that into a common representation. And similarly for DCOM, because these are mission critical environments, operators don't usually want to type the entire word decommission. So they kind of find out their own shortcuts, which they agree upon. So the role of this is to convert all commonly used phrases into a common representation. Now, given this as a knowledge base, let me show you how NetSieve understands things from its given input. Consider this example sentence. We have raised a request, blah, 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 and it is in a hung state. So the operator is describing some problematic device which is in a particular state, and then they checked the device for certain connectivity issues, and they replaced the power supply unit. That is the holistic summary of a long ticket that I scrubbed for the purpose of this presentation. This ticket in reality was close to 1,000 lines, by the way. So given this as an input, NetSieve first tokenizes that into sentences, and then finds all domain-specific phrases in the given input. For instance, here, device, power LED, amber, these are all domain-specific phrases that you don't find in regular English. Using the ontology model, it tags each of these domain-specific phrases with their respective class labels. Therefore, in the first sentence, device gets tagged as a replaceable entity, like I was mentioning before. Hung state gets tagged as a problem condition. In the second sentence, checked is a maintenance action, as you can intuitively imagine. Fiber is a replaceable entity again. And finally, faulty is a problem condition. And in the third sentence, power supply unit is tagged as a replaceable entity, upon which an action, a physical action called replaced occurred. So having this input tagged using the ontology model, let me show you how we do problem inference. Taking cues from the English grammar, we have defined a set of rules to perform this inference. The intuition is that a rule such as entity precedes or succeeds problem condition can be used to extract the problems observed in a given ticket. What do I mean by this? Let's revisit the example from the previous slide. Recall that NetSieve parsed the input, found all domain-specific words, and tagged each of them with their respective class labels. That is where we are. Now, using the first rule for finding problems, NetSieve extracts device is in a hung state, and then power supply unit is faulty as a list of problems observed in the given ticket. Similarly, using the rule for activities, it extracts that the connectivity issues have been checked and the fiber has been cleaned. And finally, using the rule for actions, it extracts that the power supply unit is replaced. The intuition is this, like entity precedes or succeeds physical action. So the entity is succeeding the physical action in this case. That is what NetSieve is actually looking for in order to extract these problems. Now that I've shown you how NetSieve operates, let me show you our evaluation results on what we did to evaluate NetSieve. Our two main goals were to evaluate NetSieve's accuracy and usability. In order to evaluate the former, we chose percentage accuracy. The paper really talks about other metrics that we used, like F-score and precision and recall. In order to evaluate the latter, we compare the time to read a ticket manually versus NetSieve inference output. For instance, if I give the same thing to an operator, how long does he take to interpret both of these things? Our dataset size is over 10,000 network trouble tickets, and as a ground truth, we have used roughly about 1,000 tickets labeled by a domain expert. So what they do is, given a ticket, they would extract problems and actions and activities from a ticket and document it somewhere, because this is the way you usually evaluate some kind of system like this. Therefore, in order to evaluate accuracy, like I was mentioning, we compare expert labeled problems and actions with that of NetSieve's inference. And in order to evaluate usability, we did a survey of 5 network operators. And to each network operator, we show about 20 tickets at random. Let me show you the evaluation results. So this slide shows you 2 graphs. The top graph is for problems. The bottom graph is for actions. The x-axis represents the category of tickets that were being evaluated. For instance, in a data center, think of it like this. Data center is made up of thousands of devices. Not all devices are like the same. They serve different roles in the data center. For instance, we have load balancers, firewalls, access routers, aggregation switches, and so on. So the x-axis represents the category of each of the tickets. The y-axis represents the percentage accuracy that was observed. Higher numbers are better. As you can see, in most of the cases, across tickets belonging to different data types, different device types, NetSieve is able to achieve a near perfect accuracy of 100%. Overall, the results are encouraging. In order to evaluate usability, we have built this as an interface for operators. The idea is we will show them a ticket initially on the left, which is a raw ticket, which contains all these raw text from operators. We will ask them to interpret the ticket and then have some kind of a notion of problems, activities, and actions. Then we will show them the output from NetSieve. So currently NetSieve supports multiple types of outputs. It can either output a table or maybe a graphical form, which is easier to interpret. So from the operator survey, we observed that NetSieve's average accuracy is about roughly 83 to 100%, in fact. And perhaps the most useful contribution of NetSieve is the significant reduction in time taken to interpret these tickets. In its 95th percentile, usually the time to read a ticket manually was close to 480 seconds. At least when I was doing this study, well, this was far higher because the sample set was higher. So my average time to read a ticket was close to about 27 minutes to just read one ticket because it contains thousands of lines. Using NetSieve, we were able to reduce this time to a mere 22 seconds. And then we deployed NetSieve in the large cloud provider that we studied. So the idea here is NetSieve, when combined with slice and dice of data essentially. So I can slice the data in different dimensions. It can provide different interesting things. The idea here is we provide different options. For instance, device types, there are different device types to which the tickets are belonging, like I was mentioning. Load balancers, core routers. The idea is that operator can actually choose each of these as filtering criteria to understand NetSiev's output. So the goal here is to not make inference from one ticket, but rather when I'm looking at thousands of tickets, what are the trends that you observe? That is what we are interested in here. And therefore we have properties. Properties are different mini teams inside the same corporate environment that own specific set of devices. Third, we have platforms. These could be from different vendors. So like a corporate never purchases the whole list of load balancers or access routers from the same vendor. They kind of have this heterogeneity to protect themselves from attacks. And finally, inference type. Do you want to observe the major problems that you have been observing or the major actions that operators take to resolve problems? The idea is we introduce what we call as trade charts to understand these kind of trends. Using these trade charts, we have made some inferences. Remember the 3 questions that I posed towards the middle of my talk? The first question was concerning redundancy. Why is it ineffective? One commonly held view is that it could be due to misconfigurations. By applying NetSieve, we found out 3 major reasons. 1, faulty cables between primary and secondary backups. Software version mismatch, and finally misconfigurations. The second question was, what are the components that fail within routers and switches? Using NetSieve, by applying them on thousands of tickets, we found line card failures, defective memory, and supervisor engine as the major contribution, as the major culprits here. The idea now is such a list of most frequently failing components or redundancy killing aspects can be used to proactively test a network for stability. That is the main utility. And the final question was, are new devices more reliable? On one hand, these devices offer high capacity and a large number of extremely good features, but do they also exhibit higher reliability? Using NetSieve, we found 2 surprising findings. First was that a newly deployed access router, which is a kind of a routing device inside data centers, was found to be only half as reliable as its predecessor. So everyone inside the network thought they were upgrading, but in fact they were downgrading in fact. And these devices are crazy expensive. The second finding was that software bugs dominated a type of load balancer failures. The surprising finding here is these bugs, which were software based, were mistaken to be hardware related problems for over a year, and the device was sent back to the vendor for replacement. Overall, operators found a high utility for NetSieve in improving network operations. Let me summarize what I have presented in this talk today. Our goal was to understand natural language text present within trouble tickets to infer 3 key features that are useful in summarizing the ticket. Towards this, we have built a system NetSieve that takes a semantic-based approach towards the problem. NetSieve combines natural language processing, knowledge discovery, and ontology modeling to extract 3 key features: problems, activities, and actions from a given ticket. We have applied NetSieve on a large ticket dataset, and the results are encouraging. Taking a step back, we're just scratching the surface here. Like I was mentioning, we're looking at only network trouble tickets and specifically for availability related issues. There's a lot more work to be done. Our aim is to motivate the research community to work on these unexplored yet important data sets, because you can draw a lot of important conclusions in your own domain. And there's a lot of work still pending to be done. For instance, one of the questions that might have occurred to you while I was presenting was, can you build the ontology model automatically? Can you reduce the role of a human when tagging these devices, when tagging these phrases? And how do you improve accuracy using, let's say, human feedback or expert feedback? And finally, can you use NetSieve in other problem domains? Sure, I used it in networking, but you could also use it in security. Like substitute every word of networking with network security and you have a different application of NetSieve. Having said that, I'd like to conclude my talk, and if you're interested in knowing more about my work, please read the paper. You can just search for Juggling the Jigsaw. That's the first half of the title. And you could also visit our project webpage, which is http://netsieve.info. I can take questions at this time. Thank you very much.
So the application that you basically build, I'm trying to see where you're trying to fit it in. Are you trying to give it to the operator so that he can understand it faster or better? Is that the usage that you're looking for?
So that's a very good question. So the utility of NetSieve is for two kind of audiences. One is operators. The other one is basically decision makers inside the corporate environment. So how would this be useful to an operator? For instance, let us say I'm a new operator. I've just joined the team. Now if a device is failing, if I have a history of known failures for the device, then I would be able to predict what could be the steps to resolve the problem. Therefore, using NetSieve, they can actually go back in time and then see what were the major problems with this particular device. So when the device last failed, what did the operator do to fix the problem? Can I repeat the same fix now? So for instance, if someone rebooted the device the previous time to fix it, can I just end up rebooting the device instead of going through the conventional way of troubleshooting everything? That is for a normal operator. The second use case is, let us assume that the operator is kind of populating the trouble tickets. The idea is NetSieve can function in an online fashion where it can keep reading the ticket, and as and when more input text comes, it can do some predictions saying that you may want to try applying these set of actions to resolve this problem. That is for an operator. The trend analysis that I showed you is for a decision maker. Oftentimes what happens is every 2 or 3 years, people called like decision makers, they go by different roles inside corporate environments. They want to know whether they have to repair or replace a given product line because things get outdated, right? At that point, it will be helpful in understanding what are the major problems that occurred for a particular device generation. For instance, think about the access router. Like if they had done this kind of an analysis before they had decided to go for a new router, they would have not gone for a replacement. At least that is the fundamental idea there.
So have you done any kind of clustering? When I say clustering, you gave an example where the lights are amber, so it could be in a boot cycle or the SMPS is down on situations like that. So have you looked at all these kind of incidences as, actually I shouldn't give the SMPS situation. So the boot cycle or the amber light, let's take that as an example. It could be the same thing on a certain device. And if you were able to build that relation and cluster it, then it becomes, you can find out the failure trends for a decision maker. Have you?
For a decision maker. So the aggregate trend analysis that I've done is doing something similar to clustering.
Okay.
Though we are not really doing any k-means there. It's not the conventional algorithm there, but essentially we're grouping tickets. So if you're familiar with SQL, then what we're doing is each of these tickets have a categorical variable saying that, okay, these tickets belong to a load balancer of this particular device model. So what we do is we apply a first phase of filtering there and then look at trend analysis on all these tickets. So,
thank you.